the Siberian to get to St. Petersburg? Okay. So this guy is given credit for discovering the periodic table, and he arranged them according to atomic mass. However, today we know that it is arranged according to atomic number. Okay, so that's as far as we got. Now let's talk about the metals, the nonmetals, and the metalloids. There is this awesome little line that kind of runs down the periodic table. It's over here. You should probably have your periodic tables in front of you. It'll be easier to see. But there is a line that goes like this. Okay? We call that the staircase. And it is separating the left and the right side of the periodic table. Most of the elements on the periodic table are metals. And I have them highlighted here in this like light green color. I think I did a pretty good job highlighting them. Okay? Down here, they are also metals. Even though I didn't highlight them, they should be right here in this spot. That's where they should be. So if you look at the atomic numbers, this is atomic number 58, and it goes all the way to atomic number 71. Well, you'll see that this skips 58 to 71. It should go right in here. And this is 90 to 103. They should go right in here. So we would have to actually split the periodic table, make it longer, and it wouldn't fit on one page. So what they did was they took it and they just took them out, stuck them on the bottom. These have names, these two rows down here, they have names. We'll get to them as we go through the notes. All right, most of the elements on the periodic table, and they are the left side of the staircase, are going to be your metals. How you're going to remember these is your favorite metal. What's your favorite metal? Iron, copper. I would probably go with gold or silver, but hey, that's just me. So your silver, your gold, they're right here. Silver, gold, platinum, copper, iron, nickel, zinc. These are all to the left of the stairs. That's why you can remember that these are your metals. Okay? On the right side of your staircase, that I have highlighted in pink over here, these are your nonmetals. Okay. And along the staircase, we're going to be getting a very big periodic table. Probably I'll do this with you tomorrow. And you're going to be coloring all these in. So just listen right now, jot a few notes, but you're going to actually be coloring in a periodic table, so you'll see exactly where they go. All of these that are sitting on top of the staircase, boron, silicon, astatine, tellurium, and arsenic and astatine, those are going to be your metalloids, germanium and antimony. Aluminum is not a metalloid. It is a true metal. Aluminum foil. Don't stick it in an electric socket. You're going to get electrocuted. Okay? So don't do that. Not a good idea. Polonium kind of goes flip-flop depending on what textbook you're reading. Polonium, in Regent's case, is not a metalloid. So it's these 5 and these 2 that are in the middle that are going to be our metalloids. Now, what makes something a metal, what makes something a nonmetal, and what makes something a metalloid? Well, metals have luster. That means they are shiny. We all like shiny things. They are shiny. All metals are shiny. So you're telling me that calcium is a metal? When I say calcium to you, what do you usually think of? Milk. That doesn't look shiny to me. Or your bones. Or stone, calcium carbonate maybe. Okay? Calcium is a metal. When it is in a compound, it doesn't have the same characteristics that I'm telling you about. So when calcium is in bones, it's not shiny. When calcium is in milk, it's not shiny because it's not elemental calcium. It's a compound of calcium. All right, it's ductile. Ductile means that it is able to be drawn, D-R-A-W-N, into wires. So if they heat it up and they pull it real fast, kind of like a piece of bubble gum. If you're chewing on bubble gum and you just pull it and you get that string that attaches the two blobs of bubble gum, metal will do the same thing when it's heated up. Okay? Malleable means if you go to a really fancy restaurant and you get leftovers and they wrap it in aluminum foil and they shape it like a swan, malleable means I can bend it or shape it into various things. So I can change the shape of a metal by bending it. Most metals bend. If you have any jewelry, ladies or gents, because this goes both ways, if you have any jewelry that's made out of gold and you're not careful with it, it will bend. You can kink gold. If you have earrings, the back of the earring will bend. If you have a bracelet, you can bend it out of shape. It is malleable. All right, metals are great conductors of electricity, and they are great conductors of heat. You know that when you're eating soup, your spoon gets hot. It's conducting heat. The heat is going from the soup to your spoon. If you blow dry your hair and you're wearing a gold necklace, that gold necklace is going to get hot, and it's going to get hot fast. They're also going to conduct electricity. And the reason why they're conducting electricity, and this is important, this is something they ask about, is because metals have electrons. They only have 1 or 2 electrons in their valence shell. That's by definition, right? They're on the left-hand side of the periodic table. They're going to have very few electrons in their valence shell. Well, those electrons move very easily. They don't want to hold on to them. They get rid of them very easily. And so those electrons are going to leave and try to find someplace else to go. Electricity is the movement of electrons. So because metals want to lose their electrons so easily, they're not holding tightly to them, those electrons are easily moved, and so therefore they are going to conduct electricity very well. Okay? They have a very special name. I'm going to write that down. They have a little phrase, because you're going to see this again. Why do metals conduct electricity? Because they have a C of mobile, that means they can move, electrons. That's why they conduct electricity. Helps if you spell it right. The electrons are constantly moving. If I have a metal and I have another metal, this metal wants to lose its electrons. It's like they're playing a giant game of hot potato because they don't want their electrons. They're giving them to somebody else as quickly as possible. So think about an atom as playing hot potato. All right. Most metals have high melting and high boiling point. Not all of them, but most of them. Can you think of a metal that doesn't have a high melting or high boiling point? Gallium. Yep. Mercury. Those are the two that popped into my brain. Okay, they both melt at very low temperatures. You can hold them in your hand. Mercury is already melted. It's already a liquid at STP. What does STP stand for? Good. And gallium just needs a little bit of heat from your body and it will disappear, or it will melt. I said disappear because there's a book called The Disappearing Spoon. Has anyone ever heard of that book? I have it someplace. The Disappearing Spoon is based on the fact that gallium, they can mold it, they can shape it. It is malleable enough to make it into a spoon, and then you put it into a glass of hot tea, and the whole spoon just disappears. It melts. All right, what are some properties of nonmetals? They're the opposite of a metal. They are dull. That means they are not shiny. They are brittle. They're going to break very easily. If you pound on them with a hammer, they're going to shatter into a million pieces. They're not going to bend like a piece of metal would. Think plastic, right? Hard, stiff plastic. All of a sudden, it goes snap, and it cracks into two different pieces. If I hit it with a hammer, it would shatter like glass into a million little pieces. So they are non-metals, brittle solids. However, a lot of nonmetals are not solid. They're going to be your gases, and there's a liquid over there too. Okay? That's because they have low melting points and low boiling points. Most of them have already reached their melting point and reached their boiling point. And finally, I know I'm out of order here, but they do not do well with conducting heat or electricity. That's why we can use plastic to insulate our hands. If you have a spoon that has plastic handle, it insulates your hand from the metal part of the spoon, and you don't burn your delicate little pinky because it was in hot soup. Okay? The metalloids are in between the metals and the nonmetals. They are sometimes referred to as semi-metals because they have some properties of metals and some properties of nonmetals. We know that they are near the staircase, sitting on the staircase, and germanium and I can't remember the other one off the top of my head. I have to look. What's the other? Antimony. Germanium and antimony. Thank you. Okay. So those are your metalloids. Any questions on where the metals are, the nonmetals, or the metalloids? I need a periodic table in front of me. Since we're talking about the periodic table, let's go grab one. Periodic table, here you are. What's up? Of course. Go ahead. Okay. So we know our metals are over here on the left. Let me stand up for a second. We know, here's my line. Let's get some. Okay, so all these guys are our metals. Is hydrogen a metal? No, it is not. It's the only one that's over there that is not a metal. All right, I want you to think about what I've taught you already about metals. Just think in your head. Think. What do you know about metals? They're shiny, they have luster, what else? Good conductors of heat and electricity. What about their electrons? They don't have a lot of valence electrons, and they get rid of them. They don't want them. Okay? Keep that in mind when I ask you this next question about the electrons. So think about the electrons in a metal. Where do you think the most reactive metal on the periodic table is located? Put your hand down for a second, Charlie. Let them think. Think back to your middle school days with Mr. Endres. He did something like this. I'm going to call on you, Charlie. Just hold on a second. Let them think. Okay, think about what Mr. Endres said. He showed you a video. Where is the most active metal? Does everybody have in their head where they think the most active metal is? Because Charlie's about to tell us where it is. Okay, go ahead. All the way on the left side. Okay, so these are the most active metals, is what you're telling me. Out of these, which one's the most active metal? Francium. Why is francium... Hey, what is this all about? Why is francium the most active metal? In terms of its electrons, Tell me why francium is the most active. It does have a lot of electrons. That doesn't make it the most active, because Rn and UUO have a lot of electrons too, but they're not active metals. Why do you think this guy is the most active metal? Think about what a metal wants to do. Think about where the electrons are located. It sure does. All these do. Give me a little bit more. You're in the right track. You're so close. Where is that one valence electron located? In its valence shell, which is where? How many rings out from the nucleus is it located? 7. Okay? So it's 7 rings out, which means that electron is way over there. And it has a lot of energy. But let's just say, let me take my little stick here. Okay? Let's just say I have electrons in 7 shells. So here's my first shell. Here's my second shell. Here's my third one. Here's my fourth one. Am I going to have room? I don't know. 5. 6. 7. Okay. I'm the nucleus, right? Here I am. That's my valence electron out here, isn't it? All the way out here. And here I am, walking around in the big wide world. Here I am. Somebody comes along, and I want to get rid of this electron. Look how far it is. If my heart, my head, my heart, my body is the nucleus, and the nucleus is positive, and it's trying to hold on to those electrons way out there, can I reach them? Why? I got so many electrons, lots of electrons, shielding this electron from my power, my positive power. I'm positive. These are negatives. So as you get further and further away, this lonely electron out here in the valence shell is not able to be held on as tightly because it is shielded, protected from the positive charge of the nucleus. Okay? So because it is so far away and it is shielded from the nucleus, that electron is given away very, very, very easily. It is the most reactive metal on the periodic table because it loses that electron the easiest. These are all active metals. They're all going to lose electrons. But lithium is not as active as francium. They get more and more. So Mr. Endres showed you a video in 7th grade. And he showed you what happens if you put lithium in water, then sodium in water. Ooh, what did I do? What did I do? What? No, it's not. I didn't know what happened. I must have hit this with my elbow. Okay, so, hey, cesium is now highlighted. We don't want cesium highlighted. There we go. So if you put all of these guys in water, this one is going to explode the most and the most violently and the fastest because it's the fastest one to get rid of that electron. Now, did Mr. Endres tell you that? He showed you sodium. Did he explain why? Did Miss Niver tell you why? No, she didn't. So now's the time in your science career to understand why you get more reactive as you move down the periodic table. So here's a question, because this is going to be asked. What happens to the metallic character That's the words they're going to use. Metallic character. As you move from top to bottom on the periodic table, are you going to get more metallic or less metallic? More. You're going to get more metallic as you go from top to bottom. What's going to happen as you go from left to right? You're going to get less metallic because your nonmetals are over here. These guys don't want to give up those electrons at all. Okay? All right. So that's that. Now, I don't know where I was. These are your nonmetals. Here's your metalloids. Okay. Any questions? You guys are moving around. Am I out of time?
Just about a minute.
A minute? All right. Remind me, tomorrow we got to do solids, liquids, and gases. Yay.